This is Algebra 2, Lesson 3-4, linear programming. Linear programming is a technique that identifies the minimum or maximum value of some quality. An objective function is the model of the quantity that you want to maximize or minimize. Constraints are limits on the variables in the objective function, and the feasible region is the region that contains all the points that satisfy the constraints. Now, some real-world problems involve multiple linear relationships. Linear programming can account for all of these linear relationships and gives the solution to the problem. The feasible region will contain all the points that satisfy the constraints. So let's take a look at some examples. The vertex principle of linear programming says if there is a maximum or a minimum value of the linear objective function, it occurs at one or more vertices of the feasible region. In other words, it will occur where lines intersect. Okay, so let's take a look at that. Let's test some vertices. What point in the feasible region minimizes p for the objective function p equals 5x plus y? And here are our constraints. Okay, constraints are your rules. Okay? If I say you have some certain constraints, if you are going to go and get a job, and I'm your parent, my constraints might be you can only work at the maximum 15 hours a week, you cannot work past 10 p.m. at night, you cannot work past midnight on weekends, and you have to put gas in the car every single time you go to work, okay, or something similar. So those would be the rules. That's what constraints means. So my constraints on my objective function are that x plus y is less than equal to 1, or x plus y is greater than or equal to 2, and x is less than or equal to 0. So if I want to see what the feasible region minimizes means smallest, lowest value. So I'm going to look at this particular equation, p equals 5x minus y, and these were the constraints. So in other words, if I was going to graph this to find a solution, I would have graphed my constraints, shaded them in the shaded region. Anything within the shaded region would be a solution to this system. But where these three lines intersected, let's just say these lines intersected like this. Whoops, let's not use highlighter. Okay, let's get rid of that. If I said that if I had a line that intersected here, then one here, then one here, and let's just say that this inside here was my shaded region, right? My vertices would be here, and these would be the things I would be testing to see if they worked. Okay? So I've graphed all of these, and let's say that these are the 4 possible points that all these constraints went to. Okay? And remember, I want to just grab this equation really quickly. P equals 5x plus y. So we're seeing if these particular vertices, which one will give us the smallest value. So let's plug in negative 1, 2 into the objective function p equals 5x minus y. So I'm going to have p equals 5 times negative 1 equals 2. So that's negative 5 minus 2, which is negative 7. And if we look at p equals 0, 2, or second one, 0, negative 2, p is going to equal 5 times 0 minus 2, so we're going to get negative 2 is the answer there. If we have 0, 1, p equals 5 times 0 minus 1, so we have negative 1 there. And the last one, p equals 5 times negative 5 minus 0. Okay, so this is going to be negative 2.5. Okay. So if I look at this, I can clearly see that the smallest value is right here. So the point that minimizes p for the objective function is negative 1, 2. Okay, so letter A is the point that minimizes p for the objective function. That's how you can find which value, if you're given a bunch of points, which value gives you the maximum or minimum. If we were looking for the maximum value, it would have been letter C. If we're looking for the minimum value, it's letter A. Okay. Linear programming got its name because it provides a plan or program that uses linear equations and inequalities. So let's take a look at using linear programming to maximize a profit. A furniture manufacturer can make from 30 to 60 tables a day and from 40 to 100 chairs a day. It can make at most 120 units, which means either chairs or tables, in one day. The profit on a table is $150 and the profit on a chair is $65. How many tables and chairs should they make per day to maximize their profit, and how much is the maximum profit? So the first thing you're going to do, if given an equation of this nature, is you're going to graph the constraints to form your feasible region. Then you're going to find the coordinates of each vertex, and then you're going to evaluate P for this particular function. So the first thing we have to do, before we can even graph the constraints, we have to get some variables. We know we're looking at tables and chairs, so I'm just going to let x equal the number of tables and y equal the number of chairs. X equals number of tables, and I'm going to let y equal the number of chairs. X equals number of tables, y equals number of chairs. They can manufacture from 30 to 60 tables a day. Okay, so now I've got to figure out my constraints. Okay. So, they can do between 30 and 60 tables a day. So, X has got to be greater than or equal to 30. But at the same time, it's got to be less than or equal to 60. I could have written that as a compound inequality. I just chose not to because it's just easier to write them separately. And then if we go back up to the question, the next thing says they can go from 40 to 100 chairs in a day. Okay, so for chairs, y is greater than or equal to 40, or y is less than or equal to 100. And then the last constraint says they can it can make at most 120 units in a day. So the number of chairs plus the number of tables has got to be a maximum of 120. So x plus y is less than or equal to 120. So there's all our constraints, which means that's what we're going to graph. There are 5 of them, and I'm just going to label them 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And I'm going to graph all 5 of these on this piece of graph paper that I have over here. Okay, just to make it easy, let's graph by 10s. 10, 20, 30, 40, 60, 70, 80, that's probably good enough there. Same thing here, and I could label my axis number of chairs and number of tables, but since I've already labeled x, what x and y are, I'm just going to label this x and this y just to save myself a little bit of space and fine. Now I'm going to graph my constraints. X is greater than or equal to 30. Remember, x equals is a vertical line, y equals is a horizontal line, which means x is greater than 30. Okay? So I'm going to have a bunch of lines here. All of these are solid lines. So x is greater than or equal to 30. That line is fine. Go for it. And greater than or equal to 30 would be this way. X is less than or equal to 60. Again, I'm going to put a line. Less than or equal to 60 is here. There's my second equation. This is 1, 2, this one goes this way. And then y is greater than or equal to 40. Greater than or equal to 40 is here, but less than or equal to 100 is here. So those two equations, that's 3, this is 4. So this one's going this way, this one's going that way. So far we have a rectangular reason we can change. The last one is x plus y is less than or equal to 20, which means if I use intercepts, I will be at 120, 120. So let's put those 2 points. So 120 here, 120 there. And that is not written in x and y equals form. So I should test a point, since it's not written in y equals form. So I'm going to have 0 is less than or equal to 120. That's true. So I would shape a 0, 0, which is here. So we'll be this side of the line. So, last but not least, let's shade it for the feasible regions. Okay, so everything I've shaded in this funny looking orange color is my feasible region. Those are all my possible solutions. However, my maximum or minimum profit will be at all these vertices, which I will put in green so you can see them. This dot here, this dot here, this dot here, this dot here. There are 4 feasible regions. So let's write down these 4 feasible regions as coordinate points. Okay. The feasible regions of the vertices are, if we look at this, 30, 40. I'm just going to go around the figure. So going more to the right, I now have 60, 40. And then I have 60, 60. And last but not least, I have 30, 90. Those are my 4 vertices. Now, if you remember, I have to get my objective function, which I haven't written yet. I wrote my constraints, but notice I never wrote my objective function. So let's go back up to this problem. The objective function is how much profit do they make on their furniture. So that would be the profit on a table is 150, and the profit on a chair is 65. So my objective function should be my profit is going to equal $150 per table plus $65 per chair. So P equals 150x plus 65y. So I'm going to use that. P equals 150x plus 65y down here, because that's my equation to maximize my profit. So now I'm just going to simply plug in what I have into my equations to see what my final answer is going to be here. So my profit here, profit is going to be 150 times 30 plus 65 times 40. If I stick that in my calculator, that's going to give me 7,100. The second equation, P equals 150 times 60 plus 65 times 40. Again, put that in your calculator, you're going to get 11,600. Profit equation for number 3 will be 150 times 60 plus 65 times 60. Profit there, 12,900. And last but not least, P equals 150 times 30 plus 65 times 90. Which will give me a profit of 10,350. So it asked me to figure out how many tables and chairs should we make per day to maximize the profit, and what is the maximum profit. Looking at this, we can see we make the most money right there. Therefore, to make the maximum profit, they should make, okay, 60 tables, 60 chairs, for a max profit of $12,000. $1,900. And that's how you use linear programming with a graph. Find your feasible regions to be able to determine your maximum or minimum quantity.